OK. So I'm going to tell you about how to get a better than 2 approximation or half approximation in the stochastic matching problem. This is joint work with my advisor, Sanjeev Khanna, and Young Lee, who was a student at Penn at that time. So, OK, so a matching is a collection of vertex disjoint edges in a graph. And in the maximum matching problem, your goal is to find the largest number of such edges in your graph, or find the largest number of matching. Now, as a notation, I'm going to use n to denote the number of vertices, and opt of g refers to size of maximum matching in graph G. We all know matching is a very fundamental problem. It's used in various applications, and as a reason, is studied also in various different models. In this talk, I'm going to look at matching in the stochastic setting. So let's define the model. Suppose you have a graph G and this probability P, and I say subgraph of G is a realization of G if I create the edges in this subgraph by picking each edge originally in G independently with probability P. So there's this process that defines the realization of G. Now, based on that, we can define the stochastic matching problem. I give you a graph G, and I tell you this is this probability parameter P, and I ask you, so now you have the graph G. Pick a sparse subgraph H of G such that the maximum matching in realization of H is a good approximation for maximum matching in realization of G. In other words, the expected value of the maximum matching in any realization of H is up to some approximation is a good representation of the expected value of maximum matching in realization of G. Let me just mention this problem was introduced originally by Blum et al. And as I show you later, it has some close ties to the kidney exchange problem. Now, as an example, you have this graph G. Then you are going to create this subgraph H of that. This subgraph is going to be fixed. This is going to be your solution. From now on, whenever I create a realization of GP, which is going to be some subgraph, it will define a unique realization in H. Just take the intersection with the edges you have in H. And so you want the maximum matching in H to be comparable in some sense to the maximum matching in G. Here, this is 3/2 approximation. Note that I cannot change the subgraph H based on each realization. I just have to create one subgraph H. OK, so I think this is a very interesting problem on its own as a theoretical problem, but it also has some nice application, in particular to this kidney exchange setting. Now here, you have these patient-donor pairs together who wants, so the patient wants to donate a kidney to the donor wants to donate a kidney to the patient, but the problem is that they are not compatible. So what is happening is that you will pair up these two pairs together such that a donor here will donate a kidney to a patient in another pair, and a donor in that pair will donate a kidney to the patient here. So this way, you can think of these pairs as vertices of a graph. And note that here, I will add an edge between any two vertices if I know that there is a possibility that exchange can happen. But this is not for sure. If I want to make sure that really an exchange can happen, I should go and perform additional tests, which are going to be expensive, to make sure that this edge will realize. But also empirically, we know that whenever there is a possibility, there is also some small, let's say, small constant probability that really this edge will realize, or you will have a chance of doing the exchange. Now, what will be the goal? Obviously, we want to get the maximum number of kidney exchange we can do, and that will correspond exactly to find a maximum matching in the underlying graph, which the edges are actually realized. At the same time, you cannot ask a patient to perform in too many expensive tests. It's time-consuming. It's going to be exhausting. And also, if you want to save on your time, you cannot wait for the result of one test before deciding on what to do next. So you have to do your test non-adaptively. And if you think about it, this is exactly what is happening in the stochastic matching problem that I said. Your subgraph H is going to be the set of edges you are going to perform the test over. OK, so hopefully I convinced you this is an interesting problem. Let's see if there are any interesting solutions to this problem also. So let's start with trivial solution. The first, most trivial answer is to just pick H to be your subgraph G. What is good about that is that you'll get the best answer possible. What is bad is that your subgraph edge may not be sparse. And if you think about it in the kidney exchange setting, you're performing tons of tests over each patient. Another extreme solution would be to fix one maximum matching in graph G and let that be your solution as subgraph edge. Now, this is quite good in terms of being sparse. This is essentially the sparsest thing you can hope for. But the problem, it's very easy to see that the best approximation factor you get is only P. And if P becomes very small, you get nothing, essentially. So the question is, can we get best of these both worlds? And what would be a good solution? I'm saying a solution is good if the degree of each vertex is some constant, possibly depending on P. And you can see easily that the dependence on P is necessary. Otherwise, you don't get anything interesting. On the other hand, I want the approximation factor that you get is independent of P. And this will be this I will consider a good solution for this problem. Do we have such solutions? And actually, yes, we know that you can get such a good result. And originally, Blum et al. Showed that you can get something close to half with a constant degree, although the degree is some large polynomial in 1 over P. Okay, and the dependence on epsilon is going to be exponential. In a work last year together again with Sanjeev and Young, we showed that actually you can get the same exact approximation factor with a very smaller degree. The degree is going to be essentially linear in P and linear in 1 over epsilon. You have this extra log term. But now our goal is to go even further than this. So we saw that there is a way to get some constant factor approximation. The real question is that what is the best constant factor approximation you can get? Or let's go for something maybe a little weaker. Can we get even something better than the previous result? And if you look at those results, they are really tailored for giving you only a half approximation. And this is a common theme in matching, really. There are these greedy algorithms that will give you half approximation, but getting better than half is slightly harder. And so the question is really, can we at least beat the half approximation factor for the stochastic matching? And our result is that, yes, indeed, we can get better than a half approximation. And so if I say the probabilities are going to be very small, think of them as being smaller than some specific absolute constant, then we get something which is slightly better than half, 0.52. And vanishingly small is really, this notion that they are smaller than some absolute constant, and it's used also in other scenarios when you work with a stochastic matching. It's just basically will make your analysis much easier. You'll get rid of lots of constant using this assumption. But even if you don't make such assumption, what we are going to show is that there is some absolute constant of order, let's say 1 over 1,000, that you are going to get an approximation which is better than half by that constant. I want to mention that, so this is beating half. In some sense, it says that half is not the correct answer, but even more important, I think, is the approach to get this result, which is going to be some sort of a structural approach instead of this greedy type of things we were doing, which I hope will have further application, at least for this problem. And just to mention one other thing is that the degree 1 we get is essentially 1 over P. We have this extra log term, but if you ignore that, that's the best degree 1 you can hope for, even if you want to get any constant factor approximation. Anything smaller than that, and basically you have tons of vertices which have no edges incident on them, which obviously you can't get any large matching in such a subgraph. So let's talk a bit about how to get this result. And let me, before that, tell you how does the previous approaches work. So the main component in the previous work is this notion of the matching cover. Think of doing this operation. Pick your graph G, pick a maximum matching from G, remove these edges, pick another maximum matching, remove the edges, and repeat this thing for, let's say, T times for some large T. And this is going to be your subgraph. And this is called the matching cover, let's say. And really, the main result we had in that paper is that if you do this operation for essentially 1 over P, or think of it as some large constant, 1,000 over P, then what is going to happen is that look at the matching you got, look at the smallest size matching you get. Suppose that matching was of size L. So it means that you were able to extract, let's say, 1,000 over P matching of size L from G. Then we prove that whenever you realize these edges, meaning that whenever you sample these edges with probability P, there is going to be also a matching of size, essentially L, in this realization. And this is really the main technical result here. There are some other techniques there, but this is the main part. So why this thing will give you two approximation easily is that suppose you run your algorithm, and the value of this parameter L, the size of the maximum matching you were extracting, is larger than half of O. In this case, we can just run the previous lemma and we'll get a matching of size half. If it is a smaller than half, what do you know? It means that you already collected half of the edges from your optimum solution. Those edges are literally inside your subgraph. So whenever you realize those edges, you are going to get the answer there also. And this is the way you are going to get a half approximation. But if you see, this is also, half is really the limit of this way of thinking, this greedy approach. This is the same case also for Blum et al. Paper. So now let's try to improve this algorithm. So let me ask you this question. If the graph G is going to have a large matching in expectation, is there going to be any specific structure in the graph G originally? Because we say that we have this graph G, we subsample its edges with probability P, and we are getting a large matching. So this should tell us something about the original graph G. Some structure should be inside G. And if this is true, then the question is that can we algorithmically exploit this structure and get results which are hopefully much better than half, hopefully, maybe not. So this question, what we can really say about the graph which has a large matching in expectation is its realization. And if you think about it, maybe intuitively at least, you hope that graph G should have lots of edge disjoint matchings, which each of them are size opt. If I have a very small number of matching of size opt and I start subsampling them at rate P, I should not be able to get anything in expectation. And this is really the main part of the argument, but because we are working with general graphs, we have to relax these things a bit. This is not going to be exactly lots of edge disjoint matching, rather one large B matching. This structure result we prove that essentially says that this intuition is correct. You will have a large 1 over P matching of size essentially opt over P in your graph G. If G is going to be, this is basically a certification that G is going to have a large matching in expectation for its realizations. And let me just mention that these bonds are tight also. You cannot get, this is the best certificate you can get using this approach. So I'm not going to talk about how to prove this thing. Let me just mention how to use this thing, really. So now, again, let's go back and look at the intuition. We prove that G has 1 over P edge disjoint matching, each of size opt. 1 over P is not enough to use it through that matching cover lemma. We said that thing requires something like 1,000 over P, some very large. And actually, the analysis is not going to get any benefit from this match. This is not the end of the story. We can use this in parallel with that other argument. So what we are going to do is to, let me just tell you the algorithm. So we are going to first pick these matchings from our original graph. We'll find a maximum 1 over P matching from the graph, take it out, then run the previous algorithm over the remaining graph, and return the both solution as our subgraph H. And the claim is that this is going to give us a better than half approximation. Okay, let me tell you a bit about how to analyze this thing. Suppose, look at the part we extracted from the matching cover algorithm. And let's realize that edges, and suppose we get this matching M. Now, you can do some sort of greedy analysis and show that if M is substantially smaller than half, I'm saying smaller than half, but it should be half minus epsilon, then you're already done. So let's assume that the matching we extracted already is only half of. Now, what is good about that is that we got a matching of size opt over 2, and we have not used any edges from the B matching we extracted already. And we know that this is this large B matching, and its edges are going to be realized independently in this problem. So let's use these edges to augment the matching we found already. So M is going to be the matching we already found, and B is going to be the B matching. So there are two cases to consider. One case is that this B matching lies completely outside the matching we gather. In this case, it's going to be very easy. You can easily prove that if you realize these edges, there is going to be also a large matching here. You can add them together to your subgraph, and you get this matching which is larger than half by some good margin. So the more interesting case is that actually most of the edges of the B matching you have are incident on the edges of your. And because the size is more than size of these B matchings are opt over P, it's going to really look like something like this. And this is the main technical claim, is that if you realize these edges, what's going to happen is that you're going to have many vertex disjoint length 3 augmenting path in your graph. And if that's the case, note that because they are vertex disjoint, I can augment all of them simultaneously, and I'll get this sort of matching. So really, all the proof goes, so you use all this idea, and you end up with proving a thing like this. Okay? That number of vertex disjoint length 3 augmenting paths are large. Now, unfortunately, the proof becomes really technical at this point. And that's the main reason we are going to lose lots of things in the constant. But on a very high level, the way to prove this is that we first formalize this, the number of possible paths, using some minimization program, which is unfortunately also nonlinear. It looks like something scary as this. With this f of p, which is some constant depending only on p, that's the main reason that our bonds differ for a smaller and larger values of p. For a very small p, this is going to be 1 only. So you'll get this minimization program, and then you have to solve this and find the optimal solution for that, and say this is the minimum number of vertex disjoint. And that's really the way we are going to get the proof for fitting half by some epsilon star margin, which is close to 2% when it's larger than 2%. When p is small enough, and otherwise it's something like 1 over 1,000. And that's the theorem. So let me just wrap up by saying that this was the first non-adaptive algorithm for the stochastic matching with approximation ratio strictly better than half. And also the degree bond in this algorithm we have is essentially optimal up to some small log factors. Now, the first obvious open problem is to really beat half by wide margins, not 2% or something much better. And I would think really we need some other forms of a structure result, or maybe just a direct use of this B matching instead of going through this algorithmic approach we use. But I think the final really interesting question here is that can we really get a 1 minus epsilon approximation with some constant degree, and really constant can be, at least theoretically, has any dependence on p and epsilon as long as it's constant. Or also, alternatively, it's very interesting to see if there is a way to prove upper bound that, OK, the non-stochastic matching problem, really, you cannot get better than some absolute constant smaller than. OK, thank you.